Today we're going to be learning about linear models. So we're actually going to look at some real-life situations in mathematics. So we have a shadow here, and the sun was directly overhead. So probably about noon, right? That's when the sun is straight ahead. The stick had no shadow. After 20 minutes, the shadow was 10.5 centimeters long, and after 60 minutes, it was 26 centimeters long. So what we have here is we need to, based on the information, estimate how long the shadow will be after 95 minutes. So I can actually see I have two sets of points here, and I can use my point slope formula. So I know that my x is going to be minutes, and my y is going to be how long my centimeters are. So my first one, I have 20 and 10.5, and my second one here, I have 60 and 26 centimeters. So what I'm going to do, if you can recall what the formula was, it was y2 minus y1 over x2 minus x1. So what I'm going to do, and I'll write it over here, is I'm going to take my y2, which is 26. So I'm going to take 26, subtract it from my 10.5, my other y, and then I'm going to take the 60 and subtract it from the 20. So 26 minus 10.5 is going to give us a cool number here. Remember, there is a decimal, so you can use your calculator. It's going to give us 15.5. And 60 minus 20 is going to give me 40. So now what you're going to do is plug in your calculator, 15.5 divided by 40, and you should get our number, or our slope for this equation, 0.3875. So this is the slope of the shadow, meaning this is what it's changing by every minute. So if I have 95 minutes, what I can actually do is take this number, 0.3875, and multiply it by my 95 minutes. Because remember, every minute it's growing 0.3875 of a centimeter every single minute. And if I have 95 minutes, we're going to get a total of 36.8125 centimeters. Meaning after 95 minutes, it's going to be 36 inches, almost 37 inches long. So now let's look at our second problem here. Oh, hey, look, it says after 95 minutes, the shadow measured 38.5 centimeters. So they did tell us if we were right or wrong. Well, we weren't technically wrong at all. We were just off. So it says, how does this compare to your estimate? So how we're actually going to compare it is take what it should be and subtract it from what we got, 36.8125. We're going to see how close we were to being exact. And remember, if we didn't get this answer, that is totally fine. We didn't even know what was going to happen. There could have been a different factor. It could have been cloudy that day. We just don't necessarily know. So we were almost a half a centimeter off, which is fine, because we didn't know what was happening, how fast the sun was going down. Maybe it was going faster and we had calculated for that, or didn't calculate for that. But remember, this is all just practice. Is the length of the shadow a function of time? Well, yes, absolutely. Yes, our shadow, remember, our shadow depends on what time it is, how long it'll be at a certain time. And it is going to be linear. Then you can say because, so yes, it's linear because we are looking at specific times. So in the example, we know at noon there was no shadow. After 20 minutes, it was 10.5. After an hour, it was 26. After 95 minutes, it was, we said about 37. It was actually 38.5. So yeah, it is the length of the shadow is a function of time, because each time interval, so 1 o'clock, 2 o'clock, and so on, the shadow is going to be different size. If you don't believe me, you go outside every hour over the weekend and measure how long your shadow is. It'll get longer or it could get shorter. We don't know yet, but that's for you to experiment. So in an earlier lesson, we saw this graph. It was talking about garbage, and this is actually a recycled graph. So it says sketch a line of function that models the change in % of garbage that was recycled between 1991 and 1995. So I'm going to look 1981 to 1995, and I'm going to try to draw out my line of best fit. Now remember, a line of best fit is kind of where almost all of the data points are either lined up or there's the same number above or below our line. So I'm going to draw it kind of right there. If yours is a little bit off, remember that's totally fine. It's just a line of best fit. So it's 1991 to 1995. And now we're going to see which years is modeling good at predicting the percentage of garbage. So we're going to look at some good years, so some great years to graph. So let's see. If I was going to try to graph something, I would probably choose 95, 96, 97, maybe like 98. So 1998 to maybe about right here, 2001. So 1998 to 2001. And then I could say another year would possibly be 2004 to maybe 4, 5, 6, 7. Somewhere in there. Now there could be a lot of possibilities. What I definitely know, because it's also asking for what years would not be the best to choose. So not the best. I would say any time that it's decreasing. So maybe like 1996 to 1998, because it's decreasing, which is fine, but it doesn't really give a good representation of data. And I would say also anything after 2013, because we don't know. If we try to draw a graph here, it's going down, which is fine, but it wouldn't best represent our data overall if we're going to look into the future. So we're going to pick a time period and sketch it. So let's do 2004 to 2007. I'm going to say would be a great year to model. So I'm going to take my pen here and kind of go like right there a little bit. You could have chosen a different one. Honestly, I could have started all the way down here at 2004, 3, 2, and went to 2011. That would have been a good one too. So, which years are not very good, we just set up there. Anything after really 2013 would not be the best. So your last part is to work on any of your checkpoints that you're missing. But I will leave it here for you and make sure you guys finish your notes.